You might think that Earth, with a diameter of about 12,742 kilometers, is something enormous when standing on its surface, but in the universe, it is really just a tiny dot that's almost insignificant. When NASA's astronauts saw this planet from orbit during the Apollo 8 mission in 1968, they didn't see a vast world, but only a fragile blue sphere floating in the endless darkness. And when we expand our view beyond the solar system, everything quickly becomes stranger, because there are stars hundreds, even thousands of times larger than our sun. The difficult thing is that the human brain is not designed to understand distances and sizes on the scale of millions or billions of kilometers. So instead of trying to imagine it immediately, let's approach this step by step with logic. And is there any limit to the size of a star or not? Let's start with something a bit more familiar, which is the sun. Because if we don't understand it, then everything that follows will become meaningless. The sun has a radius of about 696,000 kilometers and contains up to 99.86% of the total mass of the entire solar system, meaning almost everything you see orbiting it is just a very small leftover portion. If you shrink the sun down to the size of a soccer ball, about 22 centimeters, then our Earth would only be as small as a peppercorn, about 2 millimeters orbiting it. But the interesting thing is that even something as large as that is not at all special in the universe. The nearest star system to us is Alpha Centauri, about 4.37 light years away, which includes stars of sizes comparable to or slightly larger than the sun. A bit farther is Sirius A, about 8.6 light years away, with a radius about 1.7 times larger and brightness about 25 times that of the sun. These numbers show that the sun is just an average G-type star in the stellar classification system that astronomers built in the 19th century, starting from the observations of William Herschel. And when you look at all of this, you begin to realize that the size of a star is not simply a matter of how much matter it has, but also depends on deeper physical laws that govern it. And that is exactly when we need a scientific model to truly understand what is happening behind these numbers. To truly understand what is happening behind these numbers, we need a way to look at all the stars at once, instead of each one individually. And that is when the Hertzsprung-Russell diagram appears, one of the most powerful tools in astrophysics. Around 1910, two astronomers, Ejnar Hertzsprung and Henry Norris Russell, working independently, realized that if you arrange stars according to their surface temperature and luminosity, a very clear structure would emerge. On this diagram, the horizontal axis usually represents temperature, but in a somewhat counterintuitive way, from extremely hot stars over 30,000 Kelvin on the left to cool stars around 3,000 Kelvin on the right, while the vertical axis represents luminosity, from stars dimmer than the sun to stars millions of times brighter. When thousands of stars are placed on that diagram, they do not distribute randomly, but cluster into a long diagonal band. And that band is called the main sequence. This is where most stars in the universe, including our sun, spend the majority of their lifetimes. And this reflects a special stable state in stellar physics. Our sun is a G-type star with a surface temperature of about 5,778 Kelvin, located near the middle of the main sequence, not too large, not too small, not too bright. And this makes it an almost standard example for us to begin understanding other stars. But what is important is not its position on the diagram, but what is happening inside it every second. In the core of the sun, the pressure and temperature are high enough for protons to fuse through the proton-proton chain reaction, turning hydrogen into helium. And in that process, about 600 million tons of hydrogen are converted every second. A portion of this mass, about 4 million tons, is converted directly into energy according to Albert Einstein's famous equation, E_mc², and this energy creates radiation pressure that pushes outward. At the same time, the entire mass of the star creates gravitational force, pulling everything inward. And when these two forces are balanced, we have the state of hydrostatic equilibrium, which allows the star to exist stably for billions of years. This is a very important point, because it shows that a star is not a static object, but a dynamic system that constantly self-adjusts to maintain balance. If the fusion reaction increases, the star expands, reducing the temperature and slowing the reaction. And if the reaction decreases, gravity will compress the core again, increasing the temperature and accelerating the reaction. So the system always returns to the equilibrium state. But this balance is not permanent because fuel is not infinite. When the hydrogen in the core gradually depletes after millions or billions of years, depending on the star's mass, the fusion reaction gradually decreases, the outward pressure weakens, and gravity begins to dominate. The star's core contracts, and according to the law of conservation of energy, when matter is compressed, the temperature rises, potentially reaching tens of millions of Kelvin. When the temperature is high enough, a new process begins, which is the triple alpha process, in which helium fuses into carbon, and this is a major turning point in our star's life cycle. While the core contracts and heats up, the outer layers of the star react in the opposite way. They expand and cool down, making the star much larger in size, but with a lower surface temperature, causing it to turn red. This is when the star leaves the main sequence on the Hertzsprung-Russell diagram and moves up to the upper right of the diagram, entering the red giant phase, or, if large enough, red supergiant. The interesting thing is that this change is not an exception, but an inevitable part of stellar evolution. If you look at the Hertzsprung-Russell diagram as a map, you can track a star's journey from birth to death, and you will see that swelling to enormous size is a natural stage in that journey. Stars with smaller masses, like the Sun, will become red giants with sizes that can be hundreds of times their original size, while stars with larger masses can become red supergiants with sizes thousands of times larger. This means that the extremely large size of a star is not because it was born that large, but is the result of an evolutionary process lasting millions of years. And if you start thinking this way, you will realize that the question, how big is the largest star, is not just a question about size, but a question about the entire life cycle and the physical laws that govern that life cycle. Because if the size of a star can change over time, then what is important is not only how large it is, but when it reaches that size and why. And this is precisely the point where the Hertzsprung-Russell diagram becomes an indispensable tool, because it allows us not only to compare stars, but also to understand how they evolve and change over time. And when you look at this big picture, you begin to see that the monsters we are talking about are not strange exceptions, but the inevitable result of basic physical laws. But this also leads to a deeper and perhaps more interesting question. If stars can continue to swell like this during their evolution, then what really prevents them from becoming infinitely large? Or in other words, what is the ultimate limit that physics sets for the size of a star? If you start wondering what really controls that entire evolutionary process, the answer lies in an extremely basic but also very profound principle, which is the state of balance that we call hydrostatic equilibrium. A star exists not because it stands still, but because it is continuously balancing two opposing forces, acting simultaneously in every moment. On one side, you have gravity, a force very simple in nature, but extremely powerful, always trying to pull all the matter of the star closer to its center. And this force is directly proportional to the star's mass, meaning the heavier the star, the stronger the inward pull. On the other side, you have pressure generated from fusion reactions in the core, where hydrogen nuclei fuse to form helium, releasing enormous energy, and it is this energy that creates pressure-pushing matter outward. If you imagine this in a simple way, you can think of a ball being squeezed from all sides, in which gravity is like hands pressing inward, and fusion pressure is like the internal force trying to push outward, and the star only exists stably when these two forces are exactly balanced with each other. The interesting thing is that this balance is not a static state, but a continuous self-adjusting process. If for some reason the fusion reaction in the core weakens, the outward pressure will decrease, and gravity will immediately dominate, pulling matter inward and compressing the core. When the core is compressed, the temperature rises, and this accelerates the fusion reaction, thereby increasing the pressure again until balance is restored. Conversely, if the fusion reaction becomes too strong, the outward pressure will exceed gravity, causing the star to expand. When it expands, the density and temperature in the core decrease, slowing the fusion reaction, and once again the system self-adjusts to return to the equilibrium state. This is a natural negative feedback mechanism, a kind of cosmic thermostat, keeping stars stable for a very long time. And this explains why our sun can maintain a stable state for billions of years without collapsing or exploding. But the more important thing I want you to realize is that this balance depends very strongly on the star's mass. A smaller star will have weaker gravity, so it only needs a moderate level of fusion reaction to balance, and this makes it consume fuel slowly and live long. Meanwhile, a larger star has much stronger gravity, and to resist that force, it must accelerate the fusion reaction to an extremely high level, consuming fuel very quickly and becoming much brighter. This is exactly why large stars are usually brighter, but have shorter lifespans, a direct result of having to maintain balance against stronger gravity. If you push this idea a bit further, you will begin to see that a natural limit appears. If a star is too large, its gravity will be too strong, forcing the fusion reaction to occur at an extremely high rate to maintain balance, and that leads to an enormous amount of energy being released. But that energy does not simply escape outward. It creates radiation pressure, a strong pushing force that can push matter out of the star. This is where the balance begins to become fragile. If the radiation pressure becomes too great, it can overcome gravity and blow away the outer layers of the star, causing it to lose mass. And when the star loses mass, gravity decreases, changing the entire equilibrium state. This shows that not every star can maintain an arbitrarily large size, because the very mechanism that keeps it existing also limits it. One way to look at this is that each star is like walking on a tightrope, where even a slight deviation to one side will force it to self-adjust immediately to avoid collapsing or being blown apart. And this leads us to an important observation. The size of a star is not a fixed number, but the result of a continuous dynamic balance process between basic physical forces. When you understand this, you will see that the question about the largest star is not simply about finding the largest number, but about understanding which forces allow a star to reach that size, and which forces prevent it from going much further. And this is precisely the point where physics becomes interesting, because it not only describes what exists, but also explains why other things cannot exist. If you go back to the Hertzsprung-Russell diagram we just mentioned, you will see that a star's position on that diagram is actually the manifestation of this equilibrium state. Stars on the main sequence are stars maintaining balance in a stable way, while stars that leave the main sequence are stars whose balance has changed, leading to expansion or contraction. And when a star begins to expand into a red giant or red supergiant, that does not mean it becomes stronger, but that the balance inside it has changed in a way that allows the outer layers to expand very far from the core. But even in those giant states, the principle of balance still exists, only in a different, more complex and less stable form. And if you continue to follow this process, you will begin to see that every stage in a star's life cycle is a different version of this same basic principle. So, before we go further and talk about the largest stars ever observed, I want you to keep in mind a very simple but very important idea. No star exists without obeying the balance between gravity and the energy inside it, and it is this balance that both allows it to exist and sets limits for it. If you have understood that a star exists thanks to the delicate balance between gravity and pressure from fusion reactions, then the next step is to realize that there is a simple but extremely important law that governs this entire system, which is that the mass of a star determines almost every characteristic of it. In astrophysics, a surprising relationship has been found between mass and luminosity, in which luminosity does not increase linearly, but increases as a power function, usually around the third to fourth power. This means that if you take a star with 10 times the mass of the sun, you do not just have a star 10 times brighter, but it can be thousands of times brighter, sometimes up to 10,000 times, depending on its internal structure. When you look at O-type stars, the hottest and brightest stars in the universe, you see that they are only a few dozen times more massive than the sun, but they can emit energy hundreds of thousands to millions of times greater. This may sound like an advantage, as if large stars are perfect energy machines, but in reality it is completely the opposite. To maintain equilibrium against stronger gravity, these stars are forced to accelerate the fusion reaction in their cores to an extremely high level, and that means they consume hydrogen fuel at a dizzying rate. If you imagine our sun as a slow and stable engine, then these giant stars are like engines forced to run at maximum speed from the start, burning fuel so fast that they cannot sustain it for long. The result is that their lifespans are very short by cosmic standards, lasting only a few million years, sometimes even less, while our sun has a lifespan about 10 billion years and has already existed for about 4.6 billion years, while still having enough fuel to continue stably for billions more years. This difference is not random, but a direct consequence of the relationship between mass and luminosity. And it leads to a paradox that I always find interesting. The largest, brightest, and seemingly most impressive stars are precisely the ones with the shortest lives. If you look at this in a more visual way, you can think that each star is given a certain amount of fuel when it forms, and how it uses that fuel depends on its mass. A small star consumes fuel slowly, like a candle burning steadily for a long time, while a large star burns fuel like a fierce blaze that quickly dies out. This also explains why stars are usually rarer in the universe, because they do not exist long enough to accumulate in large numbers like small stars. If you observe a young star cluster, you may see a few very large and bright stars. But if you return to that cluster after a few tens of millions of years, those large stars may have disappeared, having exploded as supernovae or collapsed into strange objects like neutron stars or black holes. When you connect all of this together, you begin to see that mass not only determines size or brightness, but also determines the entire fate of a star, from how it forms, how it lives, to how it dies. And this is precisely the point where the question about the largest star becomes much more complex than just comparing sizes, because a large star not only needs to achieve that size, but also must maintain it for a long enough period for us to observe it. That means the largest stars that can exist only do so for very short periods, making them rare and difficult to detect. Therefore, when you hear about some giant star, the first thing you should ask yourself is not only how large is it, but also how long has it existed and how much longer can it exist. The greater the mass, the higher the luminosity. And when you push this relationship to its extreme, you begin to touch a boundary that physics does not allow to be crossed easily. And that is precisely where the concept of the Eddington limit becomes important. In the early 20th century, the astrophysicist Arthur Eddington tried to understand what would happen when a star became extremely luminous. And he realized that light is not simply something you see, but that it also carries momentum and can exert force on matter. In the core of a star, where fusion reactions occur intensely, energy is generated in the form of photons. And these photons continuously collide with particles in the layers of matter above, creating an outward pressure called radiation pressure. In small stars like the sun, this pressure exists but is insignificant compared to gravity, so it does not significantly alter the star's structure. However, when you increase the star's mass, you also increase the rate of fusion reactions, which dramatically boosts luminosity and therefore increases radiation pressure. At a certain point, this radiation pressure becomes large enough to directly compete with the gravitational force pulling matter inward. The Eddington limit is exactly the point where these two forces balance, where the outward radiation pressure equals the inward gravitational pull. If a star tries to become brighter than this level, the radiation pressure will exceed gravity and begin to push matter away from the star's surface. This is not a small effect, but an extremely violent process in which the outer layers of the star are blown into space at speeds that can reach thousands of kilometers per second. As a result, the star cannot retain its mass and begins to lose material. Modern observations show that very massive stars often have powerful stellar winds that can carry away an enormous amount of material each year, sometimes equivalent to the mass of Earth or more. This explains why we rarely see stars exceeding about 150 to 200 times the mass of the Sun, because as soon as they try to cross that threshold, they lose mass so quickly that they cannot maintain a larger state for long. One way to understand this is to imagine you are trying to add more fuel to a fiercely burning fire, but the fire is so strong that it blows away the very fuel you just added. In the case of stars, the light they emit is that fire, and it becomes strong enough to resist any attempt to increase mass further. This leads to a rather interesting and somewhat counterintuitive conclusion. The brighter a star is, the harder it is for it to hold itself together. In other words, light is not only a sign of power, but also a self-destructive mechanism. This is a classic example of how the universe sets its own limits through basic physical laws, where the same process both allows a system to exist and prevents it from exceeding a certain level. But the story does not end there, because the Eddington limit is not a hard wall, but a threshold that physical systems can approach in many different ways. In some special cases, such as in regions with very high matter density, or during short stages of stellar evolution, a star may temporarily exceed this limit. For example, in young star clusters where many stars form close together, collisions and mergers can create extremely massive stars for a short period before they begin to lose mass rapidly. In addition, the star's internal structure may not be uniform, and in certain regions, radiation pressure may not be distributed evenly, allowing some parts of the star to maintain larger mass for a short time. However, these states are always unstable and do not last long, and eventually the system returns below the limit due to mass loss. This shows that the Eddington limit is not a rigid rule, but a strong trend that physical systems must follow in the long term. When you look at the overall picture, you begin to see that a star's mass, luminosity, and stability are all tight linked through these basic laws. And this brings us to an important realization. The maximum size of a star does not depend only on how much material is available, but also on how well the internal forces can maintain balance before the star's own energy begins to break down its structure. This is why when we talk about the largest stars in the universe, we are not just talking about large numbers, but about systems at the edge of stability, where any small change can lead to collapse or rapid mass loss. In regions of space with extremely high density, especially in young star clusters like the central area of the Tarantula Nebula in the Large Magellanic Cloud, the distance between stars is no longer the wide light years like around the Sun, but can be much smaller, enough for gravitational interactions to become strong and frequent. When stars move in such crowded environments, the probability of collision or close interaction becomes significant, and in some rare cases, two stars can come close enough to be pulled together and merge into a single entity. When this happens, you do not simply add the masses of the two together, but you create an entirely new system with a strongly disrupted internal structure, higher temperatures, and a fusion reaction rate that can skyrocket. This is one of the mechanisms that allows the formation of stars with masses exceeding the usual limits we just discussed. And that is why we observe some stars that can reach or even exceed 200 times the mass of the Sun in special environments. A prominent example lies in the star cluster R136, where there are extremely massive stars that astronomers believe may have formed through multiple successive mergers in the early stage of the cluster. But this is where things become unstable very quickly, because as soon as you create a star with such an extremely large mass, you also push it closer to the Eddington limit we just mentioned. The radiation pressure in these stars becomes enormous. Extremely powerful stellar winds begin to blow material outward at high speeds, and the entire structure of the star becomes much more chaotic than stable main sequence stars. One way to visualize this is that you are trying to combine two engines running at full power, and the result is a more powerful system, but one that is also much harder to control. Merged stars often do not have enough time to reach a stable equilibrium state like normally formed stars, and this causes them to have very short lifespans by cosmic standards, usually lasting only a few million years. In that brief period, they can become extremely powerful sources of light, even dominating the entire surrounding star cluster, but their existence always comes with instability. Eventually, they can lose mass rapidly, collapse inward, or end in extremely violent supernova explosions, releasing so much energy that it can alter the surrounding environment over dozens of light years. The important thing I want you to realize here is that merged stars do not really break the laws in a physical sense, but they only exploit special conditions to temporarily reach states that are normally difficult to occur. The basic laws still remain, and they will quickly bring the system back within limits by forcing the star to lose mass or collapse. This is an excellent illustration of how the universe operates. It allows extreme states to exist for a short time, but does not allow them to last forever. When you look at the big picture, you begin to see that the extremely large stars we observe may not be the product of a simple process, but the result of rare and complex events like stellar mergers. This also means that when we ask about the largest star in the universe, we are not just looking for a number, but trying to understand what special conditions can create those exceptions. And as you can guess, these exceptions always come with instability, short existence times, and a bigger question. If these stars only exist for a very short time, are we seeing the whole picture or just a rare moment in a much longer process that we still do not fully understand? One of the clearest examples of how far the universe can create extreme things is the star R136A1, one of the most massive stars ever discovered, located deep within the R136 star cluster in the Tarantula Nebula of the Large Magellanic Cloud, about 160,000 light years from us. When astronomers first analyzed its light in the early 21st century, using modern telescopes like the Hubble Space Telescope, they realized that this was not a normal star, but one of the most extreme objects ever observed. Current estimates show that R136A1 has a mass of about 250 to 265 times the mass of the Sun, a number right at or even exceeding the limit we just discussed, and its luminosity can reach about 8 million times that of the Sun. If you try to imagine the amount of energy it emits every second, you will quickly realize that ordinary intuition fails, because these are no longer numbers we can perceive directly. But what makes R136A1 truly interesting is not just its mass or luminosity, but its physical size. Because although it is extremely massive and extremely luminous, its radius is only about 30 to 40 times the radius of the Sun. Compared to the red supergiants we will talk about later, this number is actually quite small, and that leads to a very important conclusion. The mass and size of a star do not always go together. A star can be extremely massive and luminous, but still relatively small if its temperature is very high, because high temperature compresses the matter and causes it to emit energy more powerfully per unit area. R136A1 is a Wolf-Rayet star, a special type of star that astronomers identify based on their light spectra, showing extremely high surface temperatures, usually over 50,000 Kelvin, and rapid mass loss through powerful stellar winds. These winds are not light breezes as we might imagine, but extremely energetic streams of material that can carry away an amount of mass equivalent to the mass of Earth in a very short time by cosmic standards. This means that although R136A1 may have formed with even greater mass in the past, it is continuously losing material and will not maintain its current state for long. When you combine all of this, you begin to see that R136A1 is not a larger version of the Sun, but an entirely different type of object. operating in a different physical regime where energy, pressure, and mass loss are all at extreme levels. This also explains why we rarely see stars like this, because they exist for a very short time before changing or ending their life cycle. And this is where the story becomes more interesting, because if you are looking for the largest star, you must clearly define what you mean, mass or size. R136A1 may be one of the most massive stars, but it is certainly not the largest star in terms of radius. This leads us to a very important distinction in astrophysics, where largest is not a simple concept but depends on how you measure it. If you care about mass, you will look for stars like R136A1. But if you care about physical size, you will have to look in a completely different place, where stars have evolved to the stage where their outer layers have expanded thousands of times their original size. When you understand this, you begin to see that the question we are pursuing is not as simple as initially imagined. And every answer opens up a new question. What we have just seen with extremely massive stars like R136A1 is only part of the story. Because to understand stars that are truly large in the geometric sense, we must look at the stage when a star begins to die, or more precisely, begins to leave its initial stable state. Throughout most of its life on the main sequence, a star maintains balance by burning hydrogen in its core. But this fuel source is not infinite, and when the hydrogen in the core gradually depletes, the fusion reaction drops to a level no longer sufficient to resist gravity. Right at that moment, the balance we talked about earlier begins to break down, and gravity, as you might guess, begins to dominate. The star's core contracts under its own weight, and as the matter is compressed, the temperature in the core rises rapidly, potentially reaching tens of millions of Kelvin. This is not just a small change, but a major turning point in the star's physics, because when the temperature reaches about 100 million Kelvin, an entirely new process begins. Helium begins to fuse through the triple alpha process to form carbon. This marks the transition from a hydrogen reactor to a helium reactor. And although this process provides energy, it does not occur in the same stable way as before. While the core is contracting and heating up, the outer layers of the star react in the opposite direction. They expand and cool down. This may sound paradoxical, but it is a direct consequence of how energy is transported within the star. As the core contracts, the energy released comes not only from the new fusion reactions, but also from the process of compressing the matter itself. And this energy travels to the outer layers, causing them to expand very far from the center. As these layers expand, their density decreases, and the surface temperature also drops, usually to around 3,000 to 4,000 Kelvin, causing the star to emit its characteristic red light. This is why we call stars in this stage red giants, or if they are large enough, red supergiants. The important thing I want you to realize is that this swelling is not because the star becomes stronger, but because its internal structure has changed in a way that allows the outer layers to escape much farther out. If you imagine a ball with a hard core and a soft shell, when the core contracts and heats up, the shell can expand very far. And that is exactly what is happening here. In the case of the sun, models show that in about 5 billion years, it will enter the red giant phase and may reach a size comparable to Earth's orbit, about 1 astronomical unit, or roughly 150 million kilometers. This means that planets like Mercury and Venus will definitely be swallowed, and Earth may be swallowed or completely incinerated by the heat and radiation. But for much more massive stars, this process is even more extreme, because they have more fuel and more complex fusion reaction stages, leading to much greater expansion. This is where the real monsters in terms of size appear, not because they have extremely large mass like R136A1, but because they are in an evolutionary stage where their structure allows them to reach enormous sizes. Another interesting thing is that in this stage, the star is no longer as stable as before, and it can experience oscillations, mass loss through stellar winds, and major changes in its internal structure. This means its size is not a fixed number but can change over time. When you connect all of this, you begin to see that the swelling of stars is not a random phenomenon, but an inevitable step in stellar evolution when the initial fuel is depleted and new reactions begin. And this is precisely the point where the question about the largest star begins to shift from considering mass to considering geometric size, because stars in this stage can become much larger than hot and massive stars like R136A1. This leads us to an important realization. To find the largest star in the universe, we should not look in places where energy is strongest, but in places where the star's structure allows it to expand to the extreme. The swelling we just mentioned reaches a very clear level when a star like the Sun enters the red giant phase, and this is the first time in its entire life cycle that size becomes the factor dominating everything else. As the core continues to contract under the influence of gravity, and the outer layers receive additional energy from within, the entire structure of the star changes in a way that if you look from the outside, you will see it swell up like a balloon being inflated. In the case of the Sun, stellar evolution models show that its radius can increase to about 1 astronomical unit, or roughly 150 million kilometers, equivalent to the current distance between Earth and the Sun. This is no longer an abstract number, because it allows you to compare it directly with the familiar solar system. If you place such a red giant in the position of the current Sun, the orbits of Mercury and Venus would lie entirely within the star's gas envelope, and these two planets would be completely swallowed. More detailed calculations show that Earth also does not have many chances of survival, because even if not swallowed directly, it would be enveloped by the expanding hot gas, subjected to extremely high temperatures and strong radiation, to the point that all forms of life and surface structures would be destroyed. The interesting thing is that while the size increases hundreds of times, the star's surface temperature decreases significantly, usually to only about 3,000 to 4,000 Kelvin, much lower than the current Sun's approximately 5,778 Kelvin. This is why these stars emit red light, because the lower temperature changes their radiation spectrum. But if you think that cooler means weaker, that is a very common misconception. Although the surface temperature decreases, the star's surface area increases enormously, and the total energy it emits, that is, its luminosity, can still be greater than before. One way to understand this is to imagine you have the same amount of energy but spread it over a much larger surface, and although each point on the surface is cooler, the total energy emitted is still very large. In reality, many red giants have luminosities hundreds to thousands of times that of the Sun, even though they appear cooler when looking at their light spectrum. Another important factor in this phase is that the star's internal structure becomes much more complex than when it was on the main sequence. Its core is no longer the only place where fusion reactions occur. Around the core there may be shells of reaction, where hydrogen continues to fuse into helium, while the inner core burns helium into heavier elements. This creates a layered structure in which each layer has different temperature and pressure conditions, and this contributes to making the outer layers less stable. It is this instability that leads to phenomena such as stellar pulsations, where the star size can change over time, and stellar winds, where material is blown into space. These winds can carry away a significant amount of mass throughout the red giant phase, changing the star's mass and structure over time. This means that the size we assign to a red giant is not a fixed number, but an average value in a system that is always changing. When you look at all of this, you begin to see that the red giant phase is not simply the star becomes bigger, but a complete restructuring of the system, where energy, pressure, and gravity interact in new ways. This is the first time in a star's life cycle that its size reaches planetary scale or even surpasses the scale of an entire planetary system. But it is important to understand that this is still not the end of the process. For relatively low-mass stars like the Sun, the red giant phase may be the peak in size before they lose their outer layers and become white dwarfs. But for much more massive stars, this phase is only a stepping stone to an even more extreme stage, where the outer layers can expand to the point that the concept of star size begins to become difficult to define precisely. Those stars will continue to evolve into red supergiants with sizes that can be thousands of times that of the Sun, enough to swallow not only nearby planets, but also most of the planetary system around them. The swelling we see in red giants is only the beginning if the star has a much larger mass than the Sun. Because for stars heavier than about 8 times the Sun's mass, the evolutionary process will go further and lead to an even more extreme phase called the red supergiant. In this phase, everything you just got familiar with in red giants is pushed to a completely different level, from size and energy to the level of instability. One of the most famous examples that astronomers often mention is Betelgeuse, a star located in the constellation Orion, about 642 light years from us, close enough for us to observe its changes directly over time. Betelgeuse has an estimated radius of about 700 to 1,000 times the Sun's radius. And if you place it at the center of the solar system, its gas envelope would expand far enough to encompass not only the orbits of Mercury, Venus, and Earth, but possibly even extend beyond Jupiter's orbit. This is no longer an abstract comparison, because it gives you a very specific image of the scale we are talking about. A star so large that it could swallow most of the planetary system around it. But what makes these stars truly special is not only their size, but their internal physical state. In a red supergiant, the star's core may be carrying out a complex chain of fusion reactions, from burning helium into carbon, then carbon into neon, oxygen, and even silicon, creating a layered structure like an onion, in which each layer performs a different reaction. This process occurs much faster than in previous stages, because each new type of fuel requires higher temperatures and is consumed more quickly. The result is that the entire system becomes extremely unstable, with outer layers that can pulsate, swell, and then contract, and continuously lose mass through powerful stellar winds. These winds can blow enormous amounts of material into space, creating clouds of gas and dust around the star. This is why when we observe Betelgeuse or other red supergiants, we often see that they do not have a perfectly round shape and exhibit fluctuations in brightness over time. A notable recent event was in 2019-2020, when Betelgeuse dimmed unusually, leading many to speculate that it might be about to explode. Although scientists later explained that the phenomenon might have been due to dust obscuring part of the light. But that event reminded us that these stars are in a state very close to their final collapse. When a red supergiant depletes the fuel in its core, it no longer has any way to maintain balance against gravity, and the core will collapse in an extremely short time, only a few seconds. This collapse leads to a supernova explosion, one of the most powerful energy events in the universe, releasing an amount of energy equivalent to all the energy the Sun will emit throughout its 10 billion year lifetime, but in just a few weeks. After the explosion, the remaining core can become a neutron star or a black hole, while the outer layers are blown into space, contributing to the creation of heavy elements such as iron, gold, and uranium. This means that the monsters we are talking about are not just large objects, but also element forges, playing an important role in forming matter in the universe. When you look at the entire process, you begin to see that a red supergiant is not just a larger version of a red giant, but a completely different state where everything happens faster, more violently, and less stably. And these are the monsters I want you to start imagining, not just because of their size, but because of the entire complexity and extremity in the way they exist and end. But even here, when you think you have seen the largest stars that can exist, the question is not over yet, because there are still other candidates even larger in size, stars that if placed in the solar system would extend far beyond what you just imagined. And that is where we will continue to delve deeper into our original question. There is one candidate that makes all previous comparisons seem almost unbelievably small, and that is UI Scuti, a star located in the constellation Scutum, about 9,500 light years from Earth, far enough that its light takes nearly 10,000 years to reach us. When astronomers analyzed observational data from infrared and optical telescopes in the early 21st century, they realized that UY Scuti was not just a normal red supergiant, but one of the largest stars ever estimated. Its radius is about 1,700 times the sun's radius. If you try to put that number into a concrete visualization, you will see that if UY Scuti were at the center of the solar system, its gas envelope would expand far beyond Jupiter's orbit and even approach Saturn's orbit. This means that the entire region of space where the large planets currently orbit the sun would lie inside a single star. When you move from radius to volume, the difference becomes even more extreme because volume increases with the cube of the radius, and that leads to a shocking number. UY Scuti could contain about 5 billion suns inside it. This is no longer a scale difference we can perceive directly, but a gap completely beyond human intuition. But what makes UY Scuti special is not only its gigantic size, but also its physical properties, which are very different from the hot and bright stars we talked about earlier. UY Scuti's surface temperature is only about 3,365 Kelvin, significantly lower than the sun's, and even much lower than O-type or Wolf-Rayet stars. This makes the light it emits primarily in the infrared region rather than visible light, and that is why it does not appear as an extremely bright star in the sky if you look with the naked eye. One way to understand this is that although the total energy it emits is very large, that energy is distributed over an extremely wide surface, reducing the light intensity per unit area. This creates an interesting contrast with stars like R136A1, where energy is concentrated in a smaller region and therefore produces extremely high luminosity. In the case of UY Scuti, you have a gigantic ball with energy spread out, making it one of the largest stars in terms of size, but not the brightest. However, there is an important point you need to note. The figure of 14,700 times the sun's radius is not an absolutely precise value, but an estimate based on models and indirect measurements. Measuring the size of a star that far away is a major challenge because we cannot see its boundary clearly, and its outer gas layers can be fuzzy and unstable. This means that UY Scuti's actual size can change over time, and different measurements can yield different results. In addition, because it is a red supergiant, it is also losing mass through strong stellar winds, and this makes its structure unstable and variable. When you combine all these factors, you begin to see that UY Scuti is not a perfect sphere with clear boundaries, but a complex system with expanding gas layers that pulsate and continuously change. This raises a very interesting question. When we say a star is the largest, what are we really measuring? The clear physical boundary, or a fuzzy gas region extending into space? But even with those uncertainties, UY Scuti is still considered one of the strongest candidates for the title of the largest star by size that we know of today. And when you look at it in the context of the entire story we have built, you begin to see a clearer picture. The largest stars are not the most massive or the brightest, but stars in a special evolutionary stage where their structure allows them to expand to the extreme. This also means that a star's maximum size is not a fixed characteristic, but a moment in its life cycle, a phase in which it may exist for a relatively short time before continuing to evolve or collapse. The deeper you go into numbers, like UY Scuti's 1,700 times the sun's radius, the more you realize that the question of largest is not only a matter of physics, but also a matter of measurement. And here, everything becomes much less certain than the appearance of the numbers. A star's size is not something we can measure directly with a ruler, but is inferred from many other quantities, the most important of which is the distance to the star. If you know how far a star is, and you measure its apparent brightness, you can infer its true luminosity, and from there estimate the size through physical models. But this entire chain of reasoning depends extremely sensitively on the accuracy of the distance. The problem is that astronomical distances are not always measured directly and with absolute precision. The most basic method astronomers use is parallax, in which a star's position is measured from two different points in Earth's orbit around the sun, creating a very small angular shift from which the distance can be calculated. This method is very effective for nearby stars within a few hundred or a few thousand light years, especially with modern missions like the European Space Agency's Gaia mission. But when you go farther, the parallax angle becomes too small to measure accurately. For stars located thousands or tens of thousands of light years away, like UY Scuti, the error in the measurement can become significant, and this directly affects all size estimates. A small deviation in distance can lead to a large deviation in radius, because the related formulas often take the form of ratios to the square or even higher powers of the distance. In addition, there are other factors that further complicate the issue, such as interstellar dust and gas that can absorb and dim the light, making the star appear fainter than it actually is, leading to incorrect estimates of luminosity and therefore size. For red supergiants, the problem is even more complex because they do not have a clear surface boundary like a solid sphere, but rather gas layers that thin out into space, making the determination of radius a concept that depends on the definition. Astronomers may define radius based on where the light drops to a certain level, but that level is not always consistent across different studies. On top of that, these stars often have pulsations and variability over time, meaning their size can change cyclically, making the determination of a single value even more difficult. When you combine all these sources of error, you begin to see that the number 1,700 times the sun's radius is not an absolute truth, but the best estimate based on currently available data and reasonable assumptions. This does not mean that scientists know nothing, but that they are working with measurements that have limits and must always account for errors. And this is precisely the point where the story becomes more interesting, because it reminds us that science is not a collection of fixed numbers, but a process of continuously refining understanding based on new data. In this context, UY Scuti may be the largest star we know of today, but it is not necessarily the largest star existing in the universe. There may be larger stars that we have not yet discovered, or current estimates may be adjusted when we have more accurate data. This leads to an important realization. When you ask what is the largest star, you are not only asking about a specific object, but about the limits of what we can measure and understand. And in many cases, the answer is not a single name, but a range of values with a certain degree of uncertainty. The uncertainty in measurement we just discussed opens up a very important possibility. UY Scuti may not be the largest star, but only the best candidate we know of at this time. And in reality, there are other objects that have been proposed that could compete for that position. One of the notable candidates is WOHG64, a red supergiant located in the Large Magellanic Cloud, about 160,000 light years from us, much farther than UY Scuti. This is a particularly interesting star, not only because of its potential size, but also because of its surrounding environment, which contains a lot of dust and gas that can affect the way we observe and measure it. Some studies, based on infrared data and radiation models, have suggested that WOHG64's radius could be equal to or even larger than UY Scuti's, placing it on the list of the largest candidates ever known. However, like the case of UY Scuti, these numbers come with a significant degree of uncertainty because of the large distance, light absorption by interstellar dust, and the inhomogeneous structure of the outer gas layers, which make determining the size extremely difficult. In the case of WOHG64, the situation is even more complicated because it is surrounded by a thick dust envelope, almost a shell of material around the star, which alters the light we receive and makes measurements heavily dependent on assumed models. This means that two different research groups, using different methods, can produce very different estimates of the size of the same star. And this is not an exception, but a fairly common situation when we study red supergiants at large distances. Besides WOHG64, there are many other stars also included in the list of largest candidates, such as VY Canis Majoris or Stephenson 218, each with different size estimates depending on the measurement method and data used. This leads to a rather interesting situation. Instead of having a clear winner, we have a group of candidates, each name representing a different set of assumptions and measurements. When you look at this from a broader perspective, you begin to see that the question of the largest star is not like finding the tallest mountain on Earth, where you can measure directly and compare, but like trying to determine the highest point in a constantly changing landscape, where measurements depend on your viewpoint and tools. And there is another possibility that is even more interesting. The largest stars in the universe may not have been discovered yet. The universe we observe is only a small part of the entire universe. And even within that part, our observational capabilities are still limited by technology, distance, and environmental conditions. Extremely large stars may exist in regions obscured by dust, or at distances too far for us to measure accurately, or exist for very short periods that make them difficult to detect. This means that the list of largest candidates we have today may only be the tip of the iceberg. When you combine all these factors, you begin to see that our original question, which seemed simple, is actually still open. Not because we lack data, but because that data always comes with errors, and because the universe is much larger than what we can observe fully. The existence of multiple candidates and the degree of uncertainty in measurements make the question of the largest star open. But that does not mean there are no real physical limits governing the maximum size a star can achieve. And one of the most important limits is the Hayashi limit, named after the astrophysicist Chushiro Hayashi. This limit is not directly related to luminosity like the Eddington limit we discussed earlier, but to the thermal structure and the way energy is transported inside a star, especially in cold and large stars like red giants and red supergiants. To understand this, you need to imagine that in large stars with relatively cool surfaces, energy from the core cannot be transported outward by radiation alone, but must go through convection, a process similar to boiling water in a pot, where hot material rises and cold material sinks. When a star expands and its surface temperature decreases, its structure becomes increasingly dependent on convection to transport energy. However, convection cannot operate effectively if the surface temperature drops below a certain level, because the temperature difference is no longer sufficient to maintain strong convective currents. The Hayashi limit is the boundary that defines the lowest temperature a star in equilibrium can maintain for a given mass. If a star tries to expand further and reduce its surface temperature below this level, the system will lose stability, because energy from the core cannot be transported outward effectively. When that happens, the star's natural response is to contract, increasing the surface temperature and restoring the ability to transport energy. This means the Hayashi limit is not a hard wall about size, but a dynamic boundary that defines the range in which a star can exist stably. For red supergiants like UI Scuti or WOHG 64, their position on the Hertzsprung-Russell diagram is often very close to the Hayashi limit, meaning they have expanded nearly to the maximum level that physics allows. This is why we do not see stars that are much cooler and much larger than what has been observed, because if they tried to cross that limit, they would not be able to maintain a stable structure and would contract. One way to understand this is to imagine you are trying to stretch a balloon to its maximum, and at a certain point, its material no longer has enough strength to hold its shape, forcing it to shrink or change structure. In the case of stars, this strength is determined by the laws of thermodynamics and fluid mechanics in plasma. The interesting thing is that the Hayashi limit depends on the star's mass, meaning larger stars can reach larger sizes before hitting this limit, but at the same time, they must also maintain higher surface temperatures to remain stable. This creates a delicate balance between size and temperature, where each star finds its position on the Hertzsprung-Russell diagram based on its mass and evolutionary state. When you combine the Hayashi limit with the Eddington limit we discussed earlier, you begin to see that two different types of limits are operating together, one related to luminosity and radiation pressure, and one related to temperature and convection. Together, they form a physical framework that defines the range in which stars can exist. This explains why, despite variations and exceptions, we still see stars concentrated in certain regions on the Hertzsprung-Russell diagram rather than distributed randomly. When you look at the big picture, you begin to see that the maximum size of a star is not an arbitrary number, but the result of multiple physical laws acting simultaneously. And the important thing is that these laws apply not only to the stars we have observed, but to all stars that can exist in the universe. This gives us a certain level of confidence that although we may not know exactly which star is the largest, we still understand the range that largest can reach. Limits like the Eddington limit and Hayashi limit are not individual exceptions, but manifestations of a broader principle in physics. No system can grow indefinitely without encountering fundamental constraints. When you look at any physical system, from a tiny particle to a giant galaxy, you will see that energy, forces, and pressure always interact in ways that lead to equilibrium or break the system if limits are exceeded. In the case of stars, we have seen this clearly through the Ballantyskratz between gravity and fusion pressure, as well as the limits of radiation pressure and convection. These principles apply not only to one specific type of star, but to all stars, regardless of whether they are large or small, hot or cold. When a star tries to become larger, it faces many different forces pulling it back toward equilibrium. And if it exceeds that level, physical mechanisms will automatically adjust to prevent further growth. This is why we do not see stars of infinite size, even though the universe seems vast and full of potential to create extreme things. One way to understand this is to imagine you are trying to pump gas into an infinite balloon, but the balloon's material can only withstand a certain pressure level before it stretches too much or bursts. In stars, this material is plasma, and the laws of thermodynamics together with gravity act as natural limits. When energy inside the star increases, it not only increases size, but also increases pressure and temperature, leading to new reactions or instability. This creates a continuous feedback loop where any growth tendency will be controlled by opposing forces. If you return to our original question about the largest star, you can see that the answer lies not only in finding a specific number, but in understanding that there is a range in which stars can exist. This range is determined by basic physical laws, and although we may not know exactly what the upper limit is, we know that it exists. This also explains why the largest stars we observe often lie near these limits, such as the Hayashi limit, but do not significantly exceed them. An interesting point is that this principle applies not only to stars, but also to many other systems in the universe, from the structure of atoms to the formation of galaxies. In every case, the balance between fundamental forces always plays a central role in determining structure and size. When you look at the bigger picture, you begin to see that the universe is not a place where everything can develop without limits, but a system finely regulated by natural laws. These laws not only restrict, but also create the diversity we observe, because they allow systems to exist in different states while still within a certain range. And precisely because of that, when we search for the largest stars, we are really exploring the limits of nature, the points where physical laws begin to manifest most clearly. This brings an interesting perspective. Instead of thinking that the universe is infinite in every aspect, we can see that it is defined by boundaries, and these boundaries themselves create structure and order. So, when you think about the monsters we have talked about, remember that they are not exceptions beyond the rules, but the most extreme examples of those rules. Our brains are not designed to process gigantic numbers or distances of millions or billions of kilometers, because throughout evolution, we only needed to understand things on the scale of a few meters or a few kilometers to survive. When you hear a number like a radius 2,700 times the sun, or a volume containing 5 billion suns, you may understand it theoretically, but you do not really feel it the way you feel the height of a building or the distance between two cities. This leads to a very subtle problem. We may unintentionally underestimate or misunderstand the scale of the universe simply because our intuition cannot keep up with the numbers. For example, when you say a star is 1,000 times larger than the sun, you might imagine it 1,000 times larger in a linear way, but in reality, its volume could be billions of times larger, because volume increases with the cube of the radius. Such distortions in intuition are very common and almost unavoidable if relying only on direct visualization. This is exactly why science does not rely only on intuition, but also on mathematics and abstract models. Mathematics allows us to work with numbers that the brain cannot visualize, and physical models allow us to describe systems that we cannot observe directly. When astronomers talk about the size of a star, they do not see it in the ordinary sense, but they infer it from light, radiation spectra, and equations describing stellar structure. This is an indirect but extremely powerful process that allows us to overcome the limitations of our senses. However, even with these tools, we are not completely free from perceptual limits. Every model we build is based on assumptions, and the way we interpret data is still influenced by the way we think. When we say a star is the largest, we are applying a very human concept to a system that may not have clear boundaries as we imagine. A red supergiant like UY Scuti does not have a hard surface like a planet, but has gas layers that gradually thin out into space, and determining where the end of the star is depends on how we define it. This shows that even when we have accurate data, the way we understand and interpret that data is still limited by the way we think. One way to look at this is that science is like a bridge between reality and our perception, where mathematics and models serve to help us approach things beyond intuition. But that bridge is not perfect and always has gaps. When you realize this, you begin to see that the question about the largest star is not only a question about physics, but also a question about how we understand the world. We can measure, calculate, and build models, but in the end, we still have to interpret those results through our own brains, a tool with limitations. This does not diminish the value of science. On the contrary, it emphasizes the importance of being aware of those limits. When we know that our intuition can be wrong, we become more careful in interpreting data and more open to results that initially seem unreasonable. And this is precisely what allows science to progress, because it's not bound by what we can easily imagine. When you connect this with everything we have said about giant stars, you will see that the challenge is not only to find the largest numbers, but to understand what those numbers mean in a universe that far exceeds our visual capabilities. Realizing the limits of personal perception is only half the story, because even when we have powerful mathematical tools and models, the data we collect is itself bound by a deeper factor: our position in the universe. We do not observe the universe from a neutral or all-powerful point, but from a specific planet orbiting a specific star in a specific galaxy. And everything we know passes through this observational window. This means that every measurement, every image, and every signal we receive is affected by distance, the interstellar environment, and even the evolutionary history of the very location where we stand. When we look at giant stars like UY Scuti or other candidates, we do not see them as they truly are, but we see their light after it has traveled thousands or hundreds of thousands of light years through space, altered by dust, gas, and gravitational fields along the way. This is the core of what scientists often call the anthropic principle, a simple but profound idea that what we can observe is limited by the conditions of our own existence. This principle does not say that the universe is designed for us, but only that if the conditions did not allow our existence, we would not be here to observe it in the first place. In the context of stars, this means we tend to observe objects and phenomena that fall within the range that our technology and position allow, and that can create an incomplete picture of the entire universe. For example, extremely large stars may exist in regions completely obscured by dust, or at distances too far for us to measure accurately, and therefore they do not appear in the data we use to build our understanding. This does not mean they do not exist, but only that they lie outside our current field of view. An important point to emphasize is that the anthropic principle does not explain why the universe has the properties it does. It is not a theory of causation, but a reminder of the limits of knowledge. It tells us that any conclusions we draw must be understood in the context of what we can observe, and that there is always the possibility of realities we have not yet accessed. When you apply this to the question of the largest star, you begin to see that the issue is not just searching within the existing data, but also realizing that this data may not represent the whole picture. There may be stars larger than any candidate we know, but they are in places where their light has not yet reached us, or are obscured, or simply have not been fully analyzed. This makes the question open, not only because of measurement errors, but also because of observational limits. When you look at the bigger picture, you begin to see that science is not a process going from not knowing to knowing completely, but a continuous process of expanding the scope of observation and understanding, always accompanied by the realization of what still lies beyond our reach. And this awareness itself, that we are limited by our conditions of existence and our position, is one of the most important limits of knowledge, because it reminds us that any answer about the universe, including the question of the largest star, must be understood as part of a larger picture that we are still exploring step by step. The observational limits we just discussed do not only affect the way we measure individual stars, but also completely change the way we perceive their place in the larger universe, because even the largest monsters we have mentioned are still very small elements in a cosmic structure that is almost beyond any ability to imagine. Let's start from the most familiar place, the Milky Way, the galaxy we live in, with a diameter of about 100,000 light years. This number is not only large, but almost impossible to visualize, because 1 light year is equivalent to about 9.46 trillion kilometers. And when you multiply that number by hundreds of thousands of times, you are talking about a distance that even light, the fastest thing we know, would take 100,000 years to cross. Inside this galaxy, there are hundreds of billions of stars, each of which can have completely different sizes, masses, and life cycles, from tiny red dwarfs to giant red supergiants like UY Scuti. But even a gigantic system like this is not the center of the universe, but only a component in a much larger picture. Beyond the Milky Way, there are hundreds of billions of other galaxies in the observable universe, each separated by distances of millions of light years, a number that already exceeds the entire size of our own galaxy. These galaxies do not exist in isolation, but often cluster together into galaxy clusters, where dozens to thousands of galaxies are bound by gravity, and these clusters in turn connect into superclusters, spanning hundreds of millions of light years. When scientists use observational tools like the Hubble Space Telescope to photograph deep regions of the universe, they see not only individual galaxies, but also larger structures, where galaxy clusters connect into enormous threads of matter, forming a network called the cosmic web. In this web, matter is not distributed evenly, but concentrated into long filaments interspersed with nearly empty voids, creating a structure that, if viewed from afar, resembles a gigantic neural network stretching across the universe. When you place the largest stars we have discussed into this context, you begin to see a profound shift in perspective. A star like UY Scuti may be large enough to swallow the orbits of Jupiter and Saturn, if placed in the solar system. But within the Milky Way, it is just one bright point among hundreds of billions of other bright points. And when you place that entire galaxy into the universe, it becomes a small dot in a collection of hundreds of billions of galaxies. This not only reduces the impressiveness of the largest stars, but also changes the way we define what is called large. An object can be extremely large on one scale, but completely insignificant on another. This is an important idea because it shows that size is not an absolute concept, but depends on the frame of reference you are using. When you only look at the solar system, a red supergiant is an unimaginable monster. But when you expand your view to the entire universe, it becomes a very small part of a much larger structure. This also helps explain why the question of the largest star does not have a definitive answer, because even if we find the largest candidate within the observable range, there is always the possibility that larger objects exist in regions we have not yet observed. More importantly, it reminds us that the universe is not organized around individual objects like stars, but around larger structures like galaxies and galaxy clusters, where stars are only small components contributing to the overall picture. When you look at this picture long enough, you begin to realize that the question, what is the largest star, is not only a question of astrophysics, but a question of how we perceive scale and our own position in the universe. It forces us to shift from focusing on individual objects to understanding the larger systems of which they are a part. And it is this change in perspective that makes the story more profound, because it not only tells you about the largest stars, but also shows you that even the largest things we can imagine are still very small parts of a universe far larger than any intuition we have ever had. The realization that even the largest stars are only a small part of the vast cosmic picture leads us to an even more important conclusion. What we know now may be only a very small part of the entire truth. There is a completely realistic possibility that stars exist that are even larger than any candidate we have discussed, but they lie beyond our current observational range, obscured by cosmic dust at distances too great, or simply exist in very short phases that make them difficult to detect. Our observational technology, although it has advanced very far, still has clear limits. Traditional optical telescopes can only see a small part of the electromagnetic spectrum, while many large stars, especially cold red supergiants, emit most of their energy in the infrared. This is exactly why modern tools like the James Webb Space Telescope are so important, because they allow us to observe the universe in the infrared band with unprecedented sensitivity and resolution, penetrating through dust clouds that previously obscured our view. Thanks to such tools, we are beginning to explore regions of the universe that were previously completely invisible, and every new observation has the potential to change our understanding of the size and distribution of stars. However, even with the most advanced technologies, we still cannot observe the entire universe. There are fundamental limits that technology cannot overcome, such as the speed of light, meaning we can only see what light has had time to reach us since the universe formed. This creates an observable universe, a region of space we can access, while the rest remains beyond our reach. In addition, even within the observable range, not every object is easy to detect, because brightness, distance, and the surrounding environment all affect observability. Extremely large stars may exist in dense star clusters or dusty regions, where their light is absorbed or scattered, making them harder to detect than their size would suggest. This means that the list of the largest stars we have today is not a complete list, but a temporary one, reflecting what we can observe with current technology. As technology improves, this list may change, with new candidates appearing and old estimates adjusted. This is not a weakness of science, but a natural part of the process of discovery, where each new generation of tools opens up a new part of the universe. When you look at this from a broader perspective, you begin to see that the question of the largest star is not only a question of physics or astronomy, but also a question of the limits of human knowledge. We can get closer to the answer, but we may never reach a completely final answer, because there is always the possibility of things we have not yet seen or understood. And it is precisely this that makes the study of the universe so interesting, because it is not a story with a clear ending, but a continuous journey, where each new discovery both answers one question and opens many more. When you accept that the unknown is still very large, you begin to see the universe not as a problem to be solved completely, but as a system gradually being explored, where each step forward expands the scope of our understanding. And in that context, the question of the largest star becomes a door leading to deeper questions about the structure, evolution, and nature of the universe we are trying to understand, the journey we have just taken, from the familiar sun to monsters like Ui Scuti, ultimately brings us back to the original question. Is this the largest star in the universe or not? And the most honest answer that science can give at this moment is that we do not know for sure. Ui-Scuti is currently one of the strongest candidates if we consider radius size, with estimates placing it among the largest stars ever recorded. But as we have seen, these numbers always come with errors, depending on distance, measurement methods, and even how we define the size of a star. Not only that, there are other candidates like W08G64 or Stephenson 218, each name carrying a different set of data and assumptions, making it nearly impossible to determine an absolute winner. And even if we could accurately determine the size of all the stars we have observed, there is still a strong possibility that other, larger stars exist beyond our current observational range, waiting to be discovered in the future. This may make you feel like the original question has no clear answer, but in fact that is precisely the strength of science. Science is not about finding a final answer and stopping. It is a continuous process of asking questions, testing hypotheses, and adjusting understanding based on new evidence. When astronomers say that Ui-Scuti is one of the largest stars we know, they are not asserting an absolute truth, but describing the best state of understanding at the present time, based on the data and technology we have. And this means the answer may change when we have more information, when new telescopes are built, or when analysis methods are improved. If you look back at the entire story, you will see that the question, what is the largest star, has actually led us through a series of deeper ideas. From how stars form and evolve, to physical limits like the Eddington limit and Hayashi limit, to the challenges of measurement and the limits of perception and observation. Each step in this journey not only brings us closer to the answer, but also opens new questions, making the picture richer and more complex. And perhaps this is the most interesting thing about science, not having all the answers, but always having new questions to explore. When you think about the universe this way, you begin to see that uncertainty is not a problem to be solved, but a natural part of the process of understanding. It allows us to keep asking questions, keep observing, and keep expanding the scope of our knowledge. So instead of viewing the lack of a definite answer as a limitation, you can see it as an opportunity, a sign that there is still so much waiting to be discovered. And in that context, the question of the largest star is not the end of the story, but a starting point, a door leading to deeper understandings of the universe. Perhaps one day we will discover a star larger than anything we know today. Or perhaps we will understand the physical limits more clearly and determine a more precise maximum range. But even if that happens, the journey of discovery will continue, because the universe is not a problem with a final answer, but an open system where each answer leads to new questions. And it is precisely in that process, in the continuous exploration and questioning, that we not only understand more about the stars, but also understand more about our own place in this vast universe. If you found this journey interesting, please hit subscribe to the channel so you don't miss the next stories about the universe we are still exploring. I will see you in the next video, where we continue to go further into the greatest mysteries of space.